Identity matrix and multiplicative inverse a to the negative 1. We're at 13.5a, and I've got 12 previous videos linked in this description, so you can watch them if you need help. Square matrices have the same number of rows as columns, and square matrices with ones from the upper left to the lower right along the main diagonal and zeros elsewhere are represented by the symbol I, the capital I. It'll look like this. See? It's got ones for the main diagonal and zeros elsewhere. And matrix I is an identity matrix. This is an identity matrix, all right? Inverses of matrices act like inverses of numbers. An additive inverse of a number is what we have to add to get the number to get 0, right? There's a multiplicative inverse that gives us a 1. So if we multiply 2 as a 2 over 1 times 1 over 2, a half, we're going to get 2 over 2, which gives us 1 whole. See? And adding or multiplying inverses always gives us the identity element for a particular operation. The additive inverse of a matrix has the same dimensions, but every element has the opposite sign. Now that's the additive inverse. And all matrices have additive inverses no matter what the dimension of the matrix. But this isn't the same with multiplicative inverses. Some matrices don't have them. Some do. So it's not the same. All matrices have additive inverses, but only some of them have a multiplicative inverse, okay? So here's our identity matrix. We've got our 1 coming down in the main diagonal. And the arrangement of an identity matrix makes sure we don't change the original matrix when we multiply any matrix by a multiplicative identity. And when we multiply two matrices, we see a change in dimension. So matrices and their inverses are always square, because we don't want to change, we can't change the dimension. So they're always square. Non-square matrices don't have multiplicative inverses. All right, so they got to be square. Suppose a matrix A has a multiplicative inverse. We can just call it an inverse. Suppose it has an inverse of a to the negative 1 power. Then this a to the negative 1 is a matrix that a times a to that negative 1 is going to equal a to the negative 1 times a. See? That's going to be an identity matrix. All right? And we can determine whether matrix A and B are inverses. So here we have matrix A and here we have matrix B. And we can test whether A times B equals B times A equals an identity matrix. We would see if it comes out like this. So if you remember how to multiply matrices, what we do is we take this 4 and then we multiply it to the negative 1/14, and then we take the 6 and multiply it to this 3/14. Do you remember how to do that? All right, so let's do this. We take this AB, and we've got a 4, a 6, a 3, and a 1. And then in B, we've got a negative 1/14, a 3/7, a 3/14, and a negative 2/7. So it'll need to equal B times A. So we put B here and A here. And that needs to equal our identity matrix, all right? So let's see if that works, and we'll do it with this one. So we're going to take this negative 1/14 and we're going to multiply it by 4. And we're going to add that to the 3/7 times the 3. See? We do this one to this one and then this one to this one. We come down the column. See? Then we do the negative 1/14 times this column, the 6, and then the 3/7 to the 1. We need to find their products and then add them. Then we do the 3/14 to the 4, and the negative 2/7 to the 3, and the 3/14 to the 6, and the negative 2/7 to the 1. We find their products and we add them. And for this one right here, we're going to get a negative 4/14 plus a 9/7. See that? 3 times 3 is 9, it's over 7. We're going to get a negative 6/14 plus a 3/7 when we do this multiplication. We're going to get a 12/14 plus a negative 6/7 when we do this one. And we're going to get an 18/14 plus a negative 2/7 when we do this one. Now we need to have them with like denominators to add them, don't we? So this would become an 18/14. And this would become a 6/14. And this would become a negative 12/14. And this would become a negative 4/14. Now when we look at them, we do our addition, we're going to get a 14/14 for this one. Negative 4 plus 18 is 14, positive 14. And this, that's a zero pair, we're going to get a 0. And here we have a 12/14 plus a negative 12/14, well that gives us another 0. And this one, 18 minus 4, well that's a 14 over 14. So look, we got our 1 and our 0 and our 0 and our 1. So this proves that A and B are inverses. So B equals A to the negative 1 and A equals B to the negative 1. It's a lot of work to prove it, but we did. Just have to remember how to do the multiplication of the matrices. And if you have a problem, there's a link to how to do that in this description. Now, we don't always know which matrices are going to turn out to be multiplicative inverses, but there's a quick way to test a 2x2 matrix. There's a theorem for it. Our next video is 13.5b, and we're going to do inverses of 2x2 matrices with that theorem. There's going to be a link to those 12 videos for Chapter 13 in this description. I'm going to add this one to the Algebra II playlist, and let's do those 2x2 matrices and find out what this quick method is that we can use. Maybe it'll save us some time. All right? I'll see you next video. Keep trying. Bye.